Here's something you've probably never noticed. Train wheels aren't cylindrical. They're not flat discs rolling on flat rails. If you look at a train wheel from the front, you'll see the running surface is slightly angled. It's conical. The wheel is wider on the inside, near the flange, and narrower toward the outside edge. The difference is subtle, maybe a few millimeters across the width of the wheel, but that tiny angle solves one of the oldest problems in rail transportation. How do you keep a train on the tracks without constantly steering it? Cars have steering wheels, ships have rudders, airplanes have control surfaces, but trains? Trains just roll. No active steering input at all. The engineer controls speed, not direction, and yet trains navigate curves, stay centered on straight tracks, and travel thousands of kilometers without derailing. The answer is in that cone, and the physics behind it is surprisingly elegant. To understand why the cone matters, let's first consider what would happen with perfectly cylindrical wheels. Imagine a train with flat, cylindrical wheels rolling on flat rails. In theory, on a perfectly straight track with perfect alignment, this would work fine. The wheels would roll forward, the train would travel straight, but real tracks aren't perfect. There are slight variations in rail alignment. There are joints where rails meet. There's thermal expansion and contraction. The train itself has play in its suspension and couplings. With cylindrical wheels, any small deviation from center would have no self-correcting force. If the train drifted slightly to the left, nothing would push it back to the right. It would just continue drifting until the wheel flange hit the rail. The flange is that raised lip on the inside edge of train wheels. It's what ultimately prevents derailment by physically blocking the wheel from sliding off the rail. But if the train relied on constant flange contact for guidance, the ride would be rough, noisy, and the wear on both flanges and rails would be severe. Cylindrical wheels would essentially bounce from flange to flange, never finding a stable center position. Now let's add the cone. A conical wheel has a larger diameter on the inside near the flange and a smaller diameter on the outside. When this wheel rolls on a rail, something interesting happens. If the wheelset, that's the assembly of two wheels connected by an axle, shifts slightly to the left wheel moves to a position where it's rolling on a larger diameter portion of its cone. The right wheel moves to a position where it's rolling on a smaller diameter portion. Here's the key insight. A wheel with a larger rolling diameter covers more distance per revolution than a wheel with a smaller rolling diameter. So when the wheel set shifts left, the left wheel wants to travel further forward per revolution than the right wheel. But both wheels are locked together on the same axle. They must rotate at the same speed. The only way to reconcile this is for the wheel set to curve back toward the right. The larger effective diameter of the left wheel pulls the assembly toward the center. If the wheel set drifts right, the opposite happens. The right wheel encounters a larger diameter. The left wheel encounters a smaller diameter, and the wheel set steers itself back toward the left. This is self-centering behavior. The conical profile creates a natural restoring force that constantly pushes the wheel set toward the center of the track. No active steering required. This phenomenon has a name: hunting oscillation, or sometimes just hunting. As a wheel set moves down the track, it actually oscillates slightly left and right, constantly correcting and recorrecting its position. The oscillation is typically small and damped by the suspension system, so passengers don't notice it. But the hunting motion is real, and it's the signature of the conical wheel doing its job. The physics here can be described mathematically, but the intuition is straightforward. Think of a cone rolling on a flat surface. If you give it a push, it doesn't roll in a straight line, it curves. The end with the larger diameter travels further than the end with the smaller diameter, so the cone traces a circular arc. Train wheels are essentially two cones joined at their bases, rolling on two parallel rails. The rails constrain the cones to stay aligned, but the conical effect still creates differential rolling radii depending on lateral position. The geometry is elegant, no power required, no sensors, no computers, just the shape of the wheel interacting with the shape of the rail. Now let's talk about curves. On a curved section of track, The outer rail has a longer path than the inner rail. If you measure the arc length, the outer rail might be several meters longer over a 90-degree turn. For a vehicle with independent wheels, like a car, this isn't a problem. The outer wheels just rotate faster than the inner wheels. The differential gear in a car's axle allows this, but train wheels are rigidly connected. Both wheels on an axle rotate at exactly the same rate. They cannot slip. How does the train navigate curves without grinding one wheel against the rail? The conical profile solves this too. When a train enters a curve, centrifugal force pushes the wheelset toward the outer rail. This shifts both wheels on their cones. The wheel on the outer rail moves to a larger diameter section. The wheel on the inner rail moves to a smaller diameter section. Now, even though both wheels rotate at the same angular velocity, they cover different distances per revolution. The outer wheel, with its larger rolling diameter, covers more ground. The inner wheel, with its smaller diameter, covers less. If the cone angle is correctly designed, the ratio of rolling radii matches the ratio of curve radii. The wheel set rolls smoothly through the curve without any slipping or grinding. This is called the rolling radius differential, and it's why trains can navigate curves that would be impossible with cylindrical wheels. The required cone angle depends on the typical curve radii the train will encounter. Higher speed trains with gentler curves can use smaller cone angles. Freight railways with tight industrial spurs might use steeper angles. Standard practice in most rail systems is a cone angle of around 120 to 140, meaning the wheel diameter changes by 1 unit for every 20 to 40 units of width. It's subtle, but it's enough. There are limits to what the conical profile can handle. Very tight curves exceed the compensation ability of the cone alone. For these situations, railways use additional techniques. Super elevation is one solution. The outer rail is raised higher than the inner rail, banking the curve like a racetrack. This reduces the centrifugal force pushing the wheel set outward and keeps the train closer to its natural running position on the cones. Check rails are another solution. These are additional rails placed near the inner wheel to guide the flange through extremely tight curves. They're common in rail yards, stations, and industrial trackage where space constraints require sharp turns. On very tight curves, some wheel slip is unavoidable and is accepted as part of normal operation. The maintenance budget accounts for increased wear in these locations, but for the vast majority of mainline railway operation, the conical wheel profile handles everything autonomously. Millions of kilometers traveled with no steering input whatsoever. The conical wheel wasn't invented overnight. It evolved through trial and error in the early days of railways. Early rail systems in mines and quarries used various wheel designs, including some with flanges on both sides and some with cylindrical profiles. The problems with these designs became apparent quickly: excessive wear, rough riding, and frequent derailments. By the mid-1800s, the single-flange conical wheel had emerged as the standard. Engineers discovered empirically that a slight cone angle made trains ride smoother and reduced maintenance costs. The mathematical explanation came later. Once the physics of differential rolling radii was understood, wheel profiles could be optimized rather than just evolved. Modern wheel and rail profile design is a sophisticated engineering discipline. The shape isn't just a simple cone. It's a complex curve optimized for wear distribution, hunting stability, curve negotiation, and noise reduction. The wheel tread typically has multiple zones: a steeper section near the flange for sharp curve negotiation, a gentler section for normal running, and specific transitions between zones to manage wheel-rail contact mechanics. Rail profiles are similarly complex. The head of the rail isn't simply flat or round. It's shaped to work with the wheel profile, distributing contact stress and managing wear patterns. When wheel and rail profiles are well matched, contact occurs on smooth, predictable surfaces. When profiles wear and become mismatched, contact becomes erratic, noise increases, and maintenance requirements rise. This is why railways have wheel truing programs. As wheels wear, they're periodically reprofiled on large lathes to restore their designed shape. A worn wheel isn't just inefficient, it can become unstable. There's an interesting phenomenon that occurs when the conical profile wears. A new wheel has its designed cone angle. As it wears from contact with the rail, material is removed from the running surface. If the wheel always runs centered, wear is concentrated in one zone, creating a hollow in the tread. This hollow changes the effective profile. The wheel no longer behaves like a simple cone. The hunting characteristics change. The curve negotiation ability degrades. In extreme cases, a hollow-worn wheel can exhibit violent hunting oscillation at speed. This is one reason why wheel condition monitoring is important. Railway maintenance programs track wheel wear and schedule reprofiling before problems develop. Modern trains often have wheel slip detection and protection systems that monitor wheel rotation and can detect abnormal behavior. While these systems primarily manage traction during acceleration and braking, they also provide data on wheel condition over time. The conical wheel is one of those elegant engineering solutions that seems obvious in retrospect, but required considerable insight to develop. The problem of train guidance could have been solved with active steering systems, with complex flange arrangements, or with tight manufacturing tolerances that kept everything perfectly aligned. All of these would have worked to some degree. Instead, the solution was a subtle shape change that harnesses basic physics. Let the wheels themselves do the steering. Let the geometry create the correction. Let the system be self-regulating. This philosophy appears throughout transportation engineering. Wherever possible, use passive stability rather than active control. Let physics work for you rather than against you. The swept wings on aircraft provide passive stability in roll. The dihedral angle creates self-correcting forces similar to what conical wheels provide for trains. The keel on a sailboat provides passive directional stability. These systems share a common insight. Clever geometry can replace complex mechanisms, so the next time you ride a train, remember what's happening beneath you. Those wheels aren't just rolling. They're constantly sensing position and making corrections. Every slight drift triggers a differential rolling response that brings the wheel set back to center. Every curve is negotiated by automatically adjusting effective diameters. No steering wheel, no computer. Just two cones on an axle, solving a problem that once seemed impossible. That's not just transportation. That's physics made practical. Speaking of self-stabilizing systems in transportation, aircraft use a surprisingly similar principle in their landing gear. The wheels are designed to caster and self-align, using geometry rather than active control. I've explained how that works in another video.